Okay, my video for today is back on UniML. Let me go to my website here. Sorry about that. View your channel. So I cover different topics, everything from battlefields of the future to AI music, and like down here, AI music, and UniML, plus other topics like wargaming and stuff. So, and I've been trying to look at category theory. So I've made several videos on that as I've just kind of discovered it. I didn't know it existed, you know, maybe a month or two ago. I can't remember. So I just kind of discovered it. That's where is it? And then started applying that to UniML, and I'm just learning category theory. So I'm making lots of mistakes, and I'm relying really heavily on Claude to UniML and category theory to keep me straight on all this. So when I make an error with category theory, it very politely but firmly says, no, it's not quite right. And on keeping you, like he says, on keeping straight, that's a standing, okay. So it gives me cautions. It says a caution. So I'm not going to read over this. Rather, I'm just going to put the link. You can see the link there, but I'll put it in my video, and you could follow along. You won't see the graphics upload, but there's not much, you can see there's not much graphics in this. So it is long conversations. And the point is that it's not just me thinking through this. I have Claude trying to watch out for my back to see if I make an error or if there's a gap in my reasoning or a flaw. And so it's keeping me straight on this. So, and I've done many chats with Claude on this, Opus, Sonnet, as each version comes out. They get, and so one chat could go search the other one, so they kind of build on each other. So given that, let me go to the topic of today's video, where the reason I started using, one of the reasons I was using Claude is I kept thinking there's a few pieces of this puzzle, UniML puzzle, that don't seem, they're either missing pieces or they're pieces kind of stuck in the wrong spot. And I've been stumped at trying to figure, I kind of sense they're there, but I can't quite direct DF on them as to what exactly, where they are and what's wrong. And here's my attempt, and category theory has helped me do that. Category theory helps me see this from a different perspective, and I think, oh, I think I'm seeing what I was doing wrong here. And so here I made this, I guess the other day, last night, I can't remember when. It was right off the press. And it's kind of messy. My handwriting's kind of bad. And I could do a PowerPoint version of this to make it look better. Like where is my, here. So yeah, I could neat it up like I had here. And use my little tangos to point things out. Like there's a arrow in category theory. There's this sort of functions as that arrow. No, that's an object. And this drawing I don't think is quite right. But the point is, I know how to do this, but it takes time to do this. So I'm not doing this on the video. I'm going back to just hand drawing. My apologies there. But so what I've looked at is different models as I go through my book, which is I've referenced. I've got several books I'm going through on category theory. So So in UniML, you have this thing called a folder. And a folder is just a collection. Like in category 3, they say it's a bag of dots. A folder is kind of a bag of pearls. And so dots have pearls. So this bag, and you can put the name of the bag. This bag is called X, capital X. And in the bag, we have 3. And these are white pearls. They're not just white pearls. They're saltwater white pearls. Because pearls have saltiness. It can be freshwater, white water, or brackish water. And they can have colors. These are all white pearls. You can have black pearls, or green pearls, or yellow pearls, or purple pearls, or blue pearls. So these are saltwater white pearls. And they all are on the diagonal. I don't show the diagonal here, but I could have. It runs like this. I'll show that here. You can see that red. This, I call it the string, and it kind of runs like a diagonal. You put bends in it. And so it's sort of like it orders things. So this comes before that on the string. And you could reorder it with things I call skywriting, but I'm not going to cover that here. So that's a little bit of a review here. So this isn't a set. It's not even really a list. It's just a bag of pearls, which you could use to model a list. And that's the idea of UniML. These are just like Tinker Toys or Lego blocks. You can use Lego blocks to build a model of, say, the space shuttle, or a barn, or whatever. And so you could use these pearls to model whatever. So the pearls they're general purpose. They can be used for anything. So you could use a folder to model a list, and a list, and then here, and this is called extension. So an extension is like a lot of times it's confusing because you can use different names for things. You can call this X, or you can call it a topological space. And they're both the same. Or you might have Abe Lincoln versus Honest Abe versus President Lincoln. They're all talking about the same thing. So you can kind of, with extensions, you could extend the naming conventions to, and it might even extend to certain traits as well, like ordered list. So this is not just a list, it's an ordered list. And I do that by adding these diamonds, so you can't really see they're diamonds, but diamonds means this follows that. They're ordered. Where here, you can change the order. They're on the string. They have an order on the string, but that's just where they happen to be on the string. They're not strictly ordered. It's like a grocery list. Buy milk, buy cheese, buy bacon. Yeah, it's ordered on the list, your piece of paper, but it doesn't mean you have to buy this first, then buy that second, buy this third. Where if you put the diamonds here, that would mean sort of, you can use that to mean, let's buy this first, this second, this third, not just they happen to be in this order on the list. So you can see how, so going from there, let's see, here I talked about brackish water white pearls. These here are brackish water white pearls, in that they define subsets. So now we're starting to use UniML to construct a mathematical set, not just a list or grocery list or just a bag of pearls. But we're saying, no, this is more than just a bag of pearls. It's modeling a set. And so one of the properties of a set is it's a subset. You can have a proper subset. So, and I've been looking at different ways of doing that. I think this is the way. Right here, I have this thing called I have things called a T-set. T-set, and let me maybe show a better version of that. You have a teacup, a saucer. This is the tea serving tray, and this is the napkin. And then and the napkin, if it goes on here, well, I'll change it to, I'll flip it, make it orange. But it's, so, and these also have functions that, like, and then this is the type of the owner. This is a freshwater white pearl. So in this folder, these are freshwater white pearls. These are saltwater white pearls. This is saltwater white pearls, and these are brackish water white pearls. And so these define these sets. So, and these landings, these things are called landings. They're how you connect. Landing means you're in my bag. You can think of it as a floor, and these are like staircases. Each one of these is a floor in a building. And that floor idea helps, category theory helps with commutability. They commute. Commute means they end up on the same floor. So if think of it as say you got a jetpack, and you're in a building, and you have a friend that has a jetpack, and you both fly from 5th floor of one building to that building could be like an object to some other building. If you land on the same floor, you've commuted. You might stop at different buildings along the way, but so this idea of floors is kind of here, and so you can kind of think these staircases are ways to get walking but down from floors. So let me go back to here. And there's a lot to cover here, and I can't review it all. So I kind of hit. So I talked about what tea sets are. So a coffee mug is a little different. It serves as something that defines an equality relationship, or maybe a greater than or equal than relationship, some sort of relationship of not just an operation, like mainly equality. So like this is greater than or equal to, or this is equal to, not a relationship like Joe likes pizza. That would be the likes would be going back to here, and these videos, explaining all this is a bit tedious here. You would use likes would be the napkin here. Joe likes pizza. And you can have the reverse here. And we'll flip this. Or it's like Jack likes Jill. And we'll reverse it. How do we reverse it? Oh, I go up here. Arrange. Rotate. So if that was Jack likes Jill, this is Jill likes Jack. So that's one kind of relationship, but a quality relationship would be more like this equals that. Like you have 2 plus 2 equals, say this is 4. 2, so you have this relationship 2, and then you'd have a different kind of, you'd have what I call a bottle water white pearl. So let's say that's 2 and that's 3. 2 plus 3 equals 5. And so you had 5 up here. You could put a coffee mug there with an equal sign. So, and yeah, you're not going to follow this, but you don't have to follow it all that much, just to follow the gist of this. Going back to here. So here, the idea is, you know, remember the details aren't important here. It's the big picture. The big picture is as we add more constructs, UniML constructs, this simple bag of pearls takes on a more richer meaning, where it could be a set. And so I think I should have put that's instead of junction box here, which means it's a member of, like this X subset, these are members of that. So so this is a set. This is a topological space, X, tau. You could have multiple topological spaces here. And so there I did put the coffee mug and says this equals that, and this means it's also a subset of that, but it's a proper subset. So and it also includes the null set. But I have that here. All sets contain the null set. And the null set, guess what? It doesn't have any junction boxes under it because it's empty. It can't. You could put even little not symbols there to say, no, can't go there. But so, and this, the proper set has all on all of these. But here, we say, let me go back to my example over here. Ooh, I'm getting myself confused. Here, these are all members, these are all objects. I'm saying these are all arrows in this subset. And actually, so I'm using, and these are river water white pearls. If it's like this, it's a bottled water white pearl. If it's like this, it's a white water white pearl. But they're all freshwater white pearls. They just take on, they have sort of different forms. But they're all all have T-sets. It kind of work mostly the same. So, and I've covered that in my other videos. So let me go back to here and this, because those are all details. The big picture here is, here we went from a simple folder to a folder that's ordered to now it's a set because we added the extra structure, like in category theory, so it's extra structure to define it. It's not just a bag of pearls, it's a bag of pearls that is where all these are a member of this, and also you have the null set is a member of this. And then here we say it's a topological space that has other things that are required. And then here I show this, we're modeling here, we're not modeling here, we're using UniML again, our logo box, to build not a full set, but to build a category, a discrete category. And so what makes it a discrete category is, see here, I have the coffee mug sitting on the saucer. Let me go back here. So you could do that. Hold on, do this. So if the coffee mug, oops. If the coffee mug, I'll just move this to here. If it's sitting on the saucer, that means that's like Joe likes Joe. So this is likes. Joe likes Joe. So Joe is both, and so the coffee mug is the subject. If this is, if you did it like this, it's a RDF. I forgot what RDF stands for, but you know, RDF is a simple sentence like Joe likes pizza. So Joe likes Joe. This would be the coffee mug is the actor, Joe. The napkin is the action, likes, and the saucer is the receiver of the action, in this case, Joe. Joe likes Joe. So, so let me go back to here. So here we have x1 dot just means this is some operator. So x1 dots with x1, and that equals x1. So we're saying x1 dot x1 equals x1. Well, that's a identity function, but this is now it's not just a set with three pearls in this bag, a bag of pearls that's now a set. It's a bag of pearls that have additional structure of arrows, and these. But actually, if you map the arrow, the white, you're saying this is not the whole arrow. The arrow has to point. The arrow has one end. It has you have an arrow from A to B, you have A, you have the arrow from A to B, and then you have B. So here you have the arrow from A to B, but it has to point to something. And so this shows you what it's pointing to. It could have been pointing to something else. It could have said A, X1, X2 points to X3. So then it would have been white pearl, the saucer here, not the saucer, the teacup here, the saucer here, and the coffee mug here. X1, X2 dot maps to X3. So here, let's see, did I look at this one here? Let me move this up a little bit here. So here, let me see, I forgot what this is. This looks like this is a category. Let's see. So here's a set X. It has elements X1. Here's my extension. So X has the equal sign here. X equals bracket X1, X2, X3. And then here's that's where we name these things. So that's kind of your lingual mode, your textual model. Down here is our structural model, where we say we're creating a bag of white pearls with X1, X2, X3. And then these are members of this set. So this is just, see, these are just words here. What do these words mean? You know, you have to have in your mind what they mean, but here they take on a meaning that UniML can understand. These are, it doesn't know what these mean. It just says, oh, there's a string of characters. Here it says, oh, this means they're in my folder. This means they're a member of this subset. And this subset is a proper, and this is the name of the subset, X. So, and then let's see, we go up here. Can I go up, catch this? There we go. And so here we say, oh, this is a membership. We say, this thing here is this little membership function. Here's my napkin ring. So we read this, X is a member of X. Oh, no. I had this wrong. This should be a proper subset here. So X is a proper subset of X. And then this white pearl down here. Oh, yeah, this one. This one would have a different, should have that napkin. It says X1 is a member of X. X2 is a member of a. So here I'm building, and then generally speaking, you could hide things here, like this is, and that's what UniML has, not UniML so much as portals, as drawing rules, where it just hides stuff that's kind of details that you can bring back up. So the moral of this whole purpose of this video is not to teach you all this stuff, because if anyone even watched this, which I doubt, they're not going to remember any of it. Rather, it's to illustrate how I'm using category theory to help me better understand the missing pieces or the wrongly placed pieces in UniML, and it's doing a good job of that. So yay, go category theory. As I learn it, it's helping me think, oh, I didn't quite have that right in UniML. And so, and as I fix this, I can use UniML to help model category theory, where I don't get it in category theory. I model it in UniML and think, oh, I understand it now. So UniML I'm using as a kind of a Rosetta Stone to understand category theory. I'm using category theory as a different perspective to look at UniML to see to fix that. And you could probably use category theory to model UniML as well, which is, though UniML, and then I thought UniML is more expressive. And what I mean by more expressive, it has more constructs. Category theory, you got two things really. You have objects and you have arrows, and you have some properties and like commutability and different properties. Meanwhile, in UniML, you have all these things. You got like swim lane islands, you got folders, you got T sets, you got tangos, you've got swim lanes and crosswalks and all this stuff. And so it gives you more visual modeling expression. You got more colors of paint, or different kinds of brushes to paint with to build your model. And I call that notational load. You have a larger notational load, meaning you have a lot more symbols here, but you have a less cognitive load. You don't have to, it's more explanatory. The picture kind of shows you what it is, so the cognitive load is less, but the notational load is more. But the notational load can be shortened by hiding things, like if you don't care about, like if we don't care about those, we can just hide them. They're gone. That reduces your notational load, but also increases your cognitive load because you have to remember, oh, they're hidden there, but we could put a string break there to hide them. So that would look kind of like this. Doop. String break. So, and then you have this little reminder here that, oops, there's something hidden here. You don't always get a string break. If you hide the contents of a folder, you don't get a string break because instead you get a different symbol. This little, I forgot what I call these little edge symbols. I covered that in a previous video. And yeah, I have trouble remembering my own stuff. So you have a little reminder there. So a little bit of cognitive load, notational load, and a little bit of cognitive load, like there's something in there, but if you open it back up, so what is that? And so you try to click on it and say unhide that. And so when you unhide it, all that comes back and you say, oh, that's what it was. Then you go hide it again. So that's the way I mean by you could have your cake and eat it. You could have low cognitive load and low notational load. And you could have high computational load by adding chips, which I could just show how you do that. Let's see, I want to add shapes. So we add a chip here. It has pins. I'm going to show the pins. So the chips with pins could take in and actually have a computational load. It could compute things. And generally the chips could be connected with white pearls or blue pearls. Blue pearls are kind of like proto white pearls. They could be birthed into a white pearl or something else. So they're generative. So you could generate new white pearls from blue pearls. They're kind of like eggs, eggs that could hatch into white pearls. So I covered all. So once again, the takeaway message is not all, well, what's this symbol here? That's a bin. What's this? That's a serving tray. What's that here? That's a slide. What's that? That's a chip. I usually fill them with nice gray color like this. And I'll put a pen on it just to show what a pen looks like. Doop, doop, doop. And you say, oh, I know what that is. It's just like, I use that kind of silver color. Here's your pen. Oops. Text fill. I want that. Home. I hate the way they do this. Here's a pen there. So it's not remember all this. It's just the thing is how one could use these Tinker toys or Lego blocks to model more complex structures just by adding more of them and arranging them a certain way to tell that story. And as you do that, you increase the notational load, but maybe decrease the cognitive load because you could see these things. They're not just abstracted or forgotten or even hidden. But once you get it, it's like, oh, I know what that is. Then you could go hide it as once you get it, you say, oh, I know what that is. Now I can hide it. If I forget what it is, I can unhide it. So, and I think, I'm not sure if this is quite all right, in that it holds water, right, internally consistent. And it may not be the best, most optimal way of doing this, whatever that means, but it is a way of doing it. And you can see it's not category theory, but it's not totally unlike category theory because you use it to model categories. So let me end the video here. And if anybody watched this all the way through from the beginning to end, kudos to you, because I can't even watch them all. But rather, I'm capturing the thoughts here, and if anybody's interested in those thoughts, well, yeah, there might be slicker, better ways to communicate those thoughts, but so far that takes more time, and I'm just wrestling with the thoughts now, not so much how to communicate them for slicker ways, but just capture them at all. So, and here it is. So this is just take it or leave it. If you leave it, that's fine. If you take it, well, maybe you could benefit from it. Maybe you could use it. Maybe you can improve on it, whatever, or find it interesting or thought-provoking. On that note, maybe it's time to end. So let me do that. Another non-award-winning video for me. So unless the award is making really boring, long-winded, chaotic videos, I might be winning that, but I doubt I'm even winning that award. So let me end here.